Welcome, this is Rob McLeod from the University of Utah and the Scientific Computing and Imaging Institute. This is the second in a series of videos explaining some of the background of UncertainSCI, and in this case, a little more of the math that goes into the software that we recently described in a workshop at the Functional Imaging and Modeling of the Heart Conference. This next talk will be by Akhil Narayan, who will get into some of the details, some of the under-the-hood mathematics that make uncertainty quantification work.
So the second half of this is going to be a little more technical. I'm going to talk to you exactly about what UncertainSCI does and how it constructs emulators. And so as a recap, here are some notational things that we decided on. P is a parameter, Q is an output. There's a distribution defined by probability density W, and we're going to form a linear emulator. So this is going to be some summation of coefficients times basis functions in P. Okay, so this is a very common approach. This itself is not polynomial chaos. It's an example of it. And since we're doing polynomial chaos, that's PC here, these functions are multivariate polynomials. So they're, x squared y or y x cubed, things like this. And we'll define the particular space that they come from. And these coefficients, these q hats, are trained more or less. So in the language of machine learning, or statistical learning, they're trained. So we had a good discussion about this just a few minutes ago about intrusive versus non-intrusive. With intrusive methods, in order to train these coefficients, I have to know a lot about the forward model. I need to know, say, what equation I'm solving, and I need to be able to manipulate it. And then I need to be able to create a new forward model that's different from the one that you already have. So intrusive methods really do require a lot of work to get them going. There are advantages of them, but they require a lot of work to get going. Non-intrusive methods, on the other hand, just require this sampling. So all I have to do is be able to provide an ensemble of data of the output at a certain design, which I'm calling P sub m, P sub lower m. And we'll talk about what that design is, but at least to do non-intrusive methods, this is all I really need. And so for the convenience reason, mainly, in UncertainSCI, we've taken the path of saying we really want to do this non-intrusively. And again, this, I think, allows us to be a lot more flexible in interfacing with a lot of software tools that people may have. And again, we're really interested in forming collaborations and trying, if you have a need for parametric uncertainty, then we think that UncertainSCI could be a great tool for that. And so we're trying to make it as accessible and non-intrusive as possible. That really is the goal. So let's talk about these two things. So I have to tell you about these polynomials phi sub j, and I have to tell you about how we train. So the polynomials come from a particular dimension n subspace. So this is now where this capital N comes from. The dimension in this case is the complexity of the emulator. So large N means I have more and more polynomial terms. And so intuitively, this just means that my emulator has greater expressivity, capacity, and that's great, except that, of course, when you have, say, a lot of degrees of freedom to figure out, then you need more training. Okay, and so this would require more data, for example. All right, so we'll talk about that in a moment, but for now, the actual basis functions look like these monomial terms. So this is a bit technical, but these lambda j's are indices. They're d-dimensional indices. Their entries are positive integers, non-negative integers. So it might be 5, 4, 0, 1 for a d equals 4 case, for example. And this would tell you the exponents on the polynomial terms. Okay, and this entire collection of all these indices, capital lambda, we're going to call that an index set. Okay, and the polynomial subspace defined by these basis functions is just the span of all these guys. Okay, and I'm going to call this V of lambda. All right. Great. So how do I define this capital lambda? What are my set of indices? In UncertainSCI, we define them with two quantities. One is an order parameter, which is basically polynomial degree. So that's something I think we're all very familiar with. So polynomial order k. And of course, large K means that you allow a lot more nonlinear effects in any one parameter, right? So naively, that means that the elements of this multi-index lowercase lambda can be very large if I allow large degree. Okay. The trade-off here, of course, is that if I make lambda very large, if I make the order very large, then this gives me a very large collection of multi-indices, which, again, as we said before, is a little more difficult to train. So there's the balancing act there. The second thing that prescribes this index set is a measure of interaction. Okay, so that is how much can parameters interact with each other in my emulator model. Okay, and again, more interactions sound like a good idea, at least allowing more interactions sound like a good idea, but this leads you into a position where you have to train more. And so, it would be nice if there's a way of suppressing interactions. Here are three common examples that we have in UncertainSCI that you'll see examples of how to define interactions. And so I've ordered them from top to bottom. These are fewer interactions to more interactions. And so these hyperbolic cross spaces are, say, the least interactive. And so I'm plotting this in the two-dimensional case, two-parameter case in this this index set plot. So this is just the plot of the first quadrant in two-dimensional space on the lattice. So these multi-indices take values on the integer lattice. And so the point is that, for example, I allow very large degree or order in the first parameter, but the trade-off is that I disallow larger orders in the second parameter. Okay, and so the only interactions I get are really these ones that have very small order in both the first and the second parameter. So that's hyperbolic cross. For total degree, that's the second one here. I allow a lot more interactions between these parameters. And of course, this is a sliding scale, and you can take things to their extreme where you allow all interactions, and that's the one on the right, which is tensor product. Okay, so these are all knobs that we have to tune in UncertainSCI. You can choose how many interactions you want, how many you need, and UncertainSCI will sort of do everything for you behind the scenes. And we'll see, I think, later today, examples of how you instantiate these particular index sets. Okay, I've already told you that having more interactions leads to a larger index set, and so leads to more things that are difficult to train. But this is a nice example everybody should do on their own once, just to convince themselves that the curse of dimensionality is real, which is that, remember, I have these three sets of index sets. So this is in reverse order. This time the TP has the most interactions. I have fewer interactions with TD, and I have very few with HC. And so this is a description of that. If I have order 2, then in 15 dimensions, tensor product has a lot of terms, a lot of interactions, but hyperbolic cross has very few. And this doesn't really get the point across. So let's just see what happens when I increase the order a little bit. And if you increase the order a little bit, then you really start to see where things can go awry if you choose large dimensions, large numbers of parameters, and high order. If you try to use something like tensor product, I mean, we're talking about numbers that are larger than GDPs of countries. Whereas if you do something like hyperbolic cross, it's still a lot, right? This is still 1,000 coefficients, 1,000 polynomials I need to learn. But at least it sounds a bit more tractable in terms of gathering data. Okay, I wish that I had a straightforward answer for everybody in terms of how should you choose what kinds of interactions to have. It's not so straightforward. This is quite a bit of an art, actually choosing these index sets. In UncertainSCI, we actually have a beta feature that automatically chooses the index set for you, but we're still testing that. Right now, we do require people to specify their interactions. We do have some nice rules of thumb that Jess, Jake, and Sumientra will probably talk to you about. But I will concede that choosing this index set is a bit of an art here. Okay. So again, when we construct these emulators, I've talked about how we choose these polynomials. How do we choose these coefficients, right? How do we actually train these coefficients? And we don't do anything fancy whatsoever. We do least squares. I'm simply going to do what's shown in the picture here. I'm going to have a bunch of data. I'm going to try to fit a curve through the data. Okay, this is really just polynomial fitting. Okay, there's nothing too fancy about this whatsoever. For mathematical reasons, we want the number of samples m to dominate the number of terms so that we can have a unique solution. And the next few slides are about answering the question, well, now that I've defined what my emulator looks like, I've defined lambda, the index set, the number of interactions, how do I generate a good design? In particular, how do I generate a good design that's robust to overfitting? Right, this is a real concern. You don't want to fit your data too closely because then you get spurious oscillations off the data points. So that's overfitting. So how do I mitigate this, or at least how do we do this in UncertainSCI? Well, the punchline is the following 2 bullet points. So we solve for these coefficients using a weighted least squares problem. I'll show you what the weight is later. And the ensemble that we generate is from a weighted de-optimal design whose candidate set is generated by induced measure sampling. Okay, so that's a lot of weird words. My hope is that in the next 5 to 10 minutes, I'll explain to you what all those words mean. And so this will make sense. But this is the punchline. This is exactly what UncertainSCI does. It simply solves a least squares problem with a particular intelligently chosen design. Okay, that's the punchline. This is at least the unweighted least squares formulation again. And so the question we really want to ask here is, how do I design this ensemble? Well, I want this to work in high dimensions. So that nixes the idea of doing something like product grids, so tensorial grids. I can't really do that in high dimensions, so I'm not going to do that. You may have heard of things like sparse grids, which are certainly a nice alternative. I think our alternative is better, and I'll be happy to discuss some math about why I think that later. But for now, the real starting point for what we do in UncertainSCI is actually fairly simple Monte Carlo sampling. So one idea might be is that, well, I'm just going to, if these parameters are uniform, I'm just going to uniformly distribute them over the domain, IID, and I'm just going to use Monte Carlo to construct this least squares emulator. This is not a new idea. It sounds really simple. So what's the problem? There isn't a problem. So in terms of the math, it turns out that this is perfectly fine. So if you define the distribution and the index set, then there is a constant C, so that if you get, and this math line that relates M and N is the critical one, if you take essentially log linear sampling, number of samples, this is almost optimal, right? So essentially the number of data points I'm asking for is basically the same as the number of unknowns that I have. There's some constants here, right, which are in red, so they probably mean something, but let's ignore them for the moment. So if I take, pretty parsimonious sampling, then you get an error estimate that's essentially the best possible one. Okay, and I really mean the mathematically best possible one. You can't do better than this. Well, we don't recover that, but we get something that's comparable to it, right? So this is really the punchline, that this sort of naive idea of doing Monte Carlo sampling actually produces something useful. Okay. The problem is what's highlighted in red, which is that this constant depends on this multi-index set and this weight, the distribution W. And what you can actually show is that this constant can be infinity in many cases. And it's pretty easy to construct an example where you see this problem in the least squares sense. So I haven't told you what the forward model is here. I'm just showing you errors. But I'm going to take 10 times as many samples as I have unknowns. And I'm going to just increase the capacity and see what happens. And there are a bunch of blue dots here because this is a random sampling procedure. So each blue dot corresponds to one trial. And the point is that, well, there's the best possible error, which is this black line. And then there's what you actually recover. And it's just completely off. And if you normalize this at this dot, if you look at this dashed line, this plot is a blow up of this dashed line. If I just increase the number of samples, and you can still see increasing number of samples doesn't seem to make the problem better. It doesn't fix it at all. Okay. So if I told you that UncertainSCI is going to do least squares using this procedure, you should be skeptical. Okay. And we don't do it using this procedure. This is simply the motivation. So how do we fix this problem? Okay. Well, it turns out the fix to this problem is not to do direct Monte Carlo sampling. It's to do biased sampling, importance sampling. Okay. So there's a new weight, a new probability density I'm going to define. And unfortunately here I see rho and p, I use the same, but I don't think there's confusion here. So rho is going to be a new probability density. It's not necessary for you to imbibe what's going on with the math here. I'll just ask you to trust me that there's a new probability density I'm defining. And it depends on the density, it depends on the prescription of the index set lambda. Okay, so I'm going to define this guy. And I'm just going to perform weighted least squares now. So now I'm going to sample not from the original density, but from this new crazy one. Okay. And of course, since I sample from a different density, I have to have a likelihood ratio in my least squares estimate to make the estimate unbiased. And that's what this new term is here. But otherwise, everything's the same. So I'm simply doing IID sampling, but now I'm doing it with importance sampling with respect to a different measure. Okay, and this seems a bit arbitrary. Why am I doing this? It turns out you entirely fixed the problem by doing this. So now there's an absolute constant C, and this absolute constant is basically order 1. I think the exact number is like 6.2 or something like this. It's a really nice number, such that you give me any distribution, you give me any index set. And strictly, if I take strict linear sampling, right? So this, again, constant C is order 1, and this is just n log n. The constant k is tunable, so you can tune it to be whatever you want. But then you just take n log n samples, and you recover, this is exactly the same statement as I had before. So this, simply by changing the way that I do sampling, you can fix this weird least squares issue. And again, in practice, you actually see this. So the left plot is the same one as I showed you before. The right one is the same problem, but now I'm just doing this weird weighted least squares sampling. Okay, and all of a sudden, the problem is completely fixed. And this behavior is true. So in fact, this kind of behavior you see in the right plot is true for any parameter dimension, for any distribution, for any index set. It's true all around the board. Okay. The real challenge that I introduced here is that, well, I seem to have gotten the great result, except that I need to sample from some weird measure that I call rho. Okay, so this is the trade-off that we have. And this measure can be very strange. So I'm just showing you here 1 and 2 dimensional, so 1 and 2 parameter versions of this density. So I guess in these top plots, the dashed blue lines are the actual density W, and the red lines are this induced distribution. Okay, so it's different, certainly. We have to sample from something else. And in 2 dimensions, it gets wonkier. If W here is the original density, then all of these other contour plots that you see here are density plots for different index sets. You can see one is hyperbolic cross, one is tensor product, one is here, one is total degree. There's this rho infinity thing, which ignore for this talk. The point really is that these measures aren't random. These new densities aren't random. We actually know empirically we know mathematically what they converge to. So that's what this rho infinity thing, it's a mathematical thing. But the point is that, these densities are very strange. And so it would be great if you had a piece of software to do all of this for you so that you don't have to worry about it. And that's exactly what UncertainSCI does. There's one other step to this. So we don't just do weighted least squares with Monte Carlo sampling. We do something that promotes a little bit more stability. So of course, when you do things randomly with Monte Carlo sampling, you can get bad draws, right? And so we want to mitigate bad draws. And we do that by solving a determinant, a de-optimal design problem, a determinant optimization problem. And there's not enough time for me today, unfortunately, to describe why this particular de-optimal design problem is the right one to do. But I'll ask you to trust me, and it has to do with the fact that we're doing induced measure sampling. So maximizing this determinant turns out to promote stability. So really, all that we do in UncertainSCI is we say, okay, well, I'm going to sample a bunch of points as candidate points from the induced measure. I'm going to solve this optimization problem, and I'm going to provide the solution of that optimization problem to the user as my ensemble of samples. Okay, so there's a big pipeline that goes on under the hood, but as a user, nobody has to care about that. This is me just trying to explain what's actually going on. As an example, here are 3 instances. So each column in this plot corresponds to a different realization, and the different rows are just different densities. So in 2D, you can see that, well, I've, I think, fairly poorly drawn contour plots of the density function. So that's what the top and bottom are. And the dots are the design that UncertainSCI requests. Okay. And so you can sort of see that, okay, for this particular density, the points are sort of uniformly distributed. For something like this beta density, this is a lot more concentrated. It's hard to see in the upper left-hand corner. But despite that fact, UncertainSCI asks for samples fairly far outside that corner. And that's not a mistake, that's by design. we need those samples outside that corner to promote numerical stability and to get these best convergence results, and basically to try to prevent overfitting. So we do all of this under the hood, but as a user, once you specify that you want a sample design, UncertainSCI is going to spit these black dots out to you. And the goal then, or really the task next, is to run a forward model on all of those simulations. So here is the same flowchart I've shown you a few times earlier today, which is how we talk about forward uncertainty. We're going to do this with UncertainSCI, in this case, with linear methods built on PC emulators. And so there are three things that UncertainSCI needs to know. One is a collection of parameters and the density associated with them. So that's something that needs to be defined. You need to describe the index set, which again is an indicator of the complexity of the emulator that you want, how many interactions there are between terms. And you need some sort of modular description of what the forward model is. That is, what's the model? It takes an input parameter and throws it out to an evaluation at that input parameter. Those three ingredients are what we need in UncertainSCI. Once UncertainSCI gets those three things, it will do some work. It'll run the forward model on that ensemble that's requested. And then it will generate an emulator from which it will compute statistics and sensitivities for you. And so all of these things on the right-hand side are done in an automated fashion once UncertainSCI finishes the work of sampling the forward model. Okay. Okay, so that is a very fast, probably, well, hopefully not too confusing rundown of what happens inside UncertainSCI. We're going to shift now in the next talk to talking more about the software itself. So we'll see that it's certainly Python, it's not intrusive, and we'll see how you can manipulate the emulator. There are some features that aren't currently in UncertainSCI that we want to get in. These are non-tensorial densities, so this means parameters that are not independent. As I described, choosing the index set, the number of interactions can be complicated, and so we'd like to simplify that and streamline that by making it adaptive. And there are some say statistical and mathematical advancements that will improve stability in terms of how we generate an ensemble. And really, in fact, all of today, we're not really going to talk about inverse problems or inference or design or optimization, but those are the really interesting and pressing problems. And so we really do want to start tackling those problems. And that's what we're planning on doing next. But right now, UncertainSCI does forward UQ analysis. So
we hope you enjoyed that video and that the explanation behind UncertainSCI will make it even more useful in your applications. We encourage you to come to our website, try out our software, and reach out to us at any time if you have questions about how to use UncertainSCI with your simulation problems.